What is a magnet? It's a hard question, right? Well, it can be described as an object that generates a magnetic field around itself, which can attract iron and some other materials. There's several types of magnet, but the one we're interested in today is called a temporary magnet. An example of a temporary magnet is something like a screwdriver, which is not normally magnetic, but if you hold it to a magnet, it can become magnetized and pick up things like paper clips. The problem with temporary magnets is that it can be hard to measure their magnetization reliably, as they often lose their magnetization to the instrument you're trying to measure it with. But there is a way, using light. This is obviously a very complex concept, so we're going to start from the basics and move up from there. So hopefully you'll learn a lot about light and magnetism along the way. Here we go. Light is a transverse wave, which means that it oscillates, in this case both in the electric and magnetic fields, perpendicular to the direction of transfer of energy. The intensity of light, so the brightness, is proportional to the amplitude, which is the maximum displacement of the center of the wave. The color is proportional to the wavelength, so the distance from one crest to the next. For example, this light will be red, for it has a long wavelength, and it would be quite dim as it has a small amplitude, whereas this light would be blue as it has quite a short wavelength, but it will be very intense as the amplitude is really quite large. Light is also a particle known as a photon. Particles are the single units that are the building blocks of our universe. Probably the most commonly known particles are the proton, the neutron and the electron, which, simply put, make up atoms. The photon is different though. It is the exchange particle for the electromagnetic force. Another example of one is the gluon, which is the exchange particle for the strong force. Photons have no mass, they are made of pure energy and move incredibly fast through space. You can imagine light as a series of boats moving through a lake in a line. The ripples represent light as a wave, and the boats represent light as a particle. Here's the confusing bit. Both the boats and the ripples are light at the same time. Whether you see light as a particle or as a wave just depends on how you look at it. If you were to look at the water level, you would see an oscillation, so you would assume light was a wave. If you were to look through binoculars, you would see the boats, so you would assume light is a particle. This has caused many arguments between physicists in the past, but it has now been proven that light is both a particle and a wave. It can be proven that light is a wave using the double slit experiment. Here you have two slits, incredibly thin and incredibly close together in an opaque material. Monochromatic laser light, or laser light of one color, is shone on the double slit. It diffracts through both, effectively forming two coherent sources. Coherent means of the same wavelength and frequency. These two sources interfere, forming interference patterns which can be seen on a screen behind the double slit. Both diffraction and interference are phenomena only seen with waves, proving that light is a wave. When we look at light as a wave, we know it oscillates. However, most light is unpolarized, meaning it oscillates not in one plane, but in many different planes. It can be often useful to us to have light that only oscillates in one plane, so we polarize it, using something called a polarizing filter. A polarizing filter is effectively a very fine grate that only lets light that oscillates at a certain angle through it. As polarizers let through all light that is oscillating at the right angle, if you place one polarizer in front of another polarizer at the same angle, a very similar amount of light will make it through. However, if you put them at 45 degrees to each other, less light will make it through, and at 90 degrees to each other, no light will make it through the polarizers. When the polarizers are in line, all the light that makes it through the first polarizer is at the correct angle to make it through the second polarizer. At 45 degrees, some of the light from the first polarizer is at too greater an angle to the second polarizer, meaning it does not pass through. When the polarizers are at 90 degrees, none of the light from the first polarizer can make it through the second polarizer. This means that if we know the amount of light making it through the polarizers, we can tell how big the angle is between the polarizers. As if a lot of light is making it through the polarizers, this suggests there is a very small angle between them. However, if there is a small amount of light making it through the polarizers, this suggests there is a very large angle between them. Remember the temporary magnetism before? We're going back to them now. We already know that temporary magnets can be magnetized or demagnetized using a magnetic field, for example from an electromagnet. Well, we can produce things called hysteresis curves from a temporary magnet. This is a graph with magnetic field strength on the x-axis and magnetization of the temporary magnet on the y-axis. You start with the magnetic field at 0, which means that the magnetization of the temporary magnet will also be 0. You then slowly increase the magnetic field until the magnetization of the temporary magnet saturates at its maximum value. You can then slowly decrease the magnetic field until the magnetization of the temporary magnet saturates at its minimum value. You can then increase it and decrease it continually, which will produce a hysteresis curve. So, how do we use all of this knowledge to work out the magnetization of a temporary magnet? We use something called the Magneto Optic Kerr effect. Here, you reflect polarized laser light off of a magnetized substance. If the substance was not magnetized, the polarization would be exactly the same before and after the reflection. However, if the substance is magnetized, the polarization changes upon reflection. As the size of this change in polarization is proportional to the magnetization of the substance, if you can find the former out, you can work out the magnetization of a temporary magnet. To use this effect, you need a laser, an initial polarizer, the magnetic substance near an electromagnet, an analyzer, which is a type of polarizer commonly used in computer screens, and some form of light probe. Light from the laser is polarized by the initial polarizer. This light is then reflected by the substance which has been magnetized by the electromagnet. This light then passes through the analyzer and onto the light probe. As the polarizer and the analyzer are set to the same plane of polarization, when there is no rotation of polarization, all the light from the polarizer makes it through the analyzer. However, when the substance is magnetized, meaning the polarization is rotated, less light will make it through the analyzer. This change can be detected by the light probe. Therefore, the lower the signal detected by the light probe, the larger the rotation of the polarization. So therefore, the larger the magnetization of the substance. To vary the magnetization of the substance, you can then vary the strength of the magnetic field produced by the electromagnet, and plot this against the signal recorded by the light probe. This should give you, with a little bit of manipulation, the hysteresis curve you want. This has been an explanatory physics video. I have been Joseph Copland, and you have been a good listener. Thanks a lot for watching and hopefully enjoying this. I'll see you guys later. Goodbye.